Can you see two clusters in these points? Kind of, sort of. So what are the two clusters? There is a row of pluses there and the row of pluses at the bottom. So there are two clusters here, right? So I will not touch these data points, right? I will just do the following. Now do you see two clusters? Side by side. So what essentially defines clusters is not the distance between the data points, right? It is more like the density of the data points, right? Naturally when we think of clusters, it is really things that where data points are really dense is one cluster, and then we tend to draw the boundary between clusters where the density is lower, right. So I did not change the data points. In the initial set of data points you are very happy to say that okay, the clusters are at the top and at the bottom, right. So what caused you to change your clustering when you added the additional data points? The density went up, right. The density went up in a different way. So therefore you said, oh okay, the least dense point is no longer between the two but vertically, right. No longer horizontal but vertical was the low density points, right.
If you run k-means you will get it.
If you run k-means you might get anything, I do not know, right, depending on where you start off with, right. So the question is, so if your intuitive notion of clustering is to do with density, so why do not you try to come up with a clustering algorithm that captures this notion of density, right. And try to come up with a clustering algorithm that captures this notion of density. So there is a very popular clustering algorithm called DB-scan, right, very popular algorithm called DB-scan that does density based clustering, okay. So DB-scan actually has a lot of terminology that they define, right. Once all the terminology is defined, then the clustering algorithm itself becomes nearly trivial, okay, but the terminology takes a while to get through, okay. So the basic idea is very simple, right. Suppose I have a suppose I have data points like this, right. Do you see two clusters here? Clearly two clusters, right. Incredibly hard to get k-means return these two clusters to you. But if you run k-means, what will happen is you will end up with a centroid somewhere here, right, another centroid somewhere here, right, and it will say these data points are one cluster and these data points are another cluster. Right, this is the biggest drawback with k-means, right. So what DB-scan says is that 2 points belong to the same cluster, okay. If I can get from one point to another, right, by moving only through dense regions, right, only through points that are close by, right. 2 points belong to the same cluster, right. Suppose I take let's say I take this point, right, and I take this point, right. In fact they look pretty far away, right. If you look at the direct distance between them, they are pretty far away. In fact the points of other cluster which are closer to this than this point, right. But when you look at it, you think that hey, this thing is one cluster, this thing is another cluster. So what is the intuition here is that okay, I can keep hopping right, no point do I take a very big hop, right, I can keep hopping to things that are nearby and I can go from here to here, right. So if I take these 2 points, the blue and the brown one, right. So if I take these 2 points, there is no way I can hop from here to here, right, because there is this nice gap here, right. There is no way I can get from here to here only by going through dense regions, right. Is that clear? So that is the intuition that we are trying to capture here. So what is it that we should define now first? What I mean by a dense region, right. So that is essentially what we have to define. So we will start off by defining something called a, there are two parameters that DB-scan uses. One is called min points, the other one is epsilon. Okay, these are two parameters. So min points essentially gives you some kind of a threshold on how many points would you consider as being dense, right, and epsilon gives you the area over which you will perform the count, right. So min point says, okay, if you have 5 points, okay, then you are in a dense neighborhood, but where do I count these 5 points? Okay, in a radius of epsilon around me, you count the 5 points, okay, you count in the area of epsilon around me. If you find 5 points, then you are in a dense region, right. If you make the epsilon very large, then it might encompass my entire input space, then everybody will be dense, so it does not make sense, right. The epsilon has to be small, right. Likewise, if I make my min points 1 point, 1 or 2 points, that means everything will look dense, right, unless I make my epsilon very small. So these are actually complementary things. I can control my min points, right. I can make the min points very small, right, and then make the density high, right, or I can make my min points large with a larger epsilon, and then also I can make my density high. Okay, the effects that you will see are different for both, right. So I will let you think about it, which one, I mean, what is the effect of increasing min points versus decreasing epsilon. Okay. So essentially what I am saying is, okay, take a data point, right, take a radius epsilon around it, okay, that's a circle, okay. So take a radius epsilon around it and count the number of points, okay. Okay, if this count is greater than min points, okay, then you call this a core point. Okay, take a data point, take a ball of radius epsilon around the data point, right, count the number of points, right. If the number of points is greater than or equal to min points, right, number of points is greater than or equal to min points in that ball of epsilon, then you call this a core point, right. A core point is a point that lies in a high density region, that is the definition we have, right. So we say a point is you see that a point is density reachable, okay, a point is density reachable if there is a core point, okay, from which you can reach this point, right, by traversing only through core points. So this might not be a core point because it is at the border, right. I draw a radius around it, I get only one point here, okay. So this might not be a core point, right, but then if I start here, let us say this is a core point for sure, because a lot of points in the thing. From here, okay, I can basically move to points within epsilon of itself, right, which are in turn core points, right. So I can move to core points, right, and finally reach this, right. So at no point I should be making a jump greater than epsilon, right, because if I start in a core point I will have enough points in the neighborhood that I can actually jump to something within epsilon, right. So I make steps of size epsilon and I actually go through core points every time, okay. Then we call them density reachable, right. So a point I is density reachable if there exists a core point from which I can reach here by jumping only from a core point to core point until the last step. And obviously every core point is density reachable because it is reachable from itself, right, every core point is density reachable, and then there will be these border points, right, which are density reachable from core points. Okay. There might be other points which are not density reachable from core points, which are essentially outliers. Okay. Right. So these are the definitions we have. So this is the first. Right. These are the two quantities we need. This is okay. These are not definitions. This is the first definition. What is a core point? Second definition. Third definition is density connected. Okay, so I will say 2 points I and j are density connected if there exists a core point k from which both of them are density reachable. That makes sense, right. So what is density reachable? I start from a core point and only move to core points, right, until I make the last hop to this guy. So no point I will be making a move greater than epsilon, and all the points I visit in the on the way will be core points. Okay, that is density reachable. Density connected is if I and j there exists one core point from which both I and j are density reachable, then the I and j are density connected. Okay. Here is the next thing. So I and j are in the same cluster if and only if they are density connected. Yeah, this is the definition of a cluster. 2 points I and j belong to the same cluster if and only if they are density connected. Make sense? Sorry, how do I implement this? So I start off with any point, right? I pick up a random point, right? I figure out whether it's a core point or not, right? Then okay, okay, if it's a core point, great. So I'll keep that as my starting point for the cluster. How do I determine it's a core point? I pick up a point, look in the neighborhood, figure out if there are epsilon, I mean if there are min points within a neighborhood of epsilon. If that is the case, then I'll keep it, right? Then what I do is I look at all the neighbors of that point. And I look at all the neighbors of the point, and each point in turn I will check whether it is a core point or not. Right. So each point in turn I will check if it is a core point or not. So any additional points I encounter when I do this check, I will throw it into my queue. So I will keep going. Right. If I reach a point which is not a core point, okay, so I will not insert the neighbors of that new neighbors of that point, I will just stop there. If I reach a point it is not a core point, I will just leave that exploration, go back to my queue to see if anything else is still there. So I keep doing this until my queue becomes empty. So all the points I have examined from the time I started till my queue became empty go into a single cluster.
Isn't that depth first search?
Sorry?
Isn't that depth first search?
It's like a depth first search, yeah. It's like a depth first search. You do that, all these data points go to a single cluster. Now what I do, I go and start at a random point which has not been assigned a cluster so far, and then do the depth first search again till I find the whole cluster. So I do this and I am done. So the nice thing about this is I am really doing only one scan through the data, right. So every data point I will actually look at it once, right. I will examine the neighborhood, right. And then I will go on, but then the number of computation I will do will be still significant. So DB scan is a slow algorithm, even though I examine each data point only once, but the amount of computation I do when I examine a data point is significant, because I am looking at the radius epsilon and then I have to find all the neighbors within the radius. So unless I have a very efficient data structure that will return to me the nearest neighbors very quickly, right. So this can take a significant amount of time in running. So there are some efficient implementations of DB scan out there. It is really cool in that it gives you all kinds of arbitrary clusters, right. And so these kinds of things, right, whatever I drew there, that you would not be able to recover using k-means or even hierarchical clustering, depending on the kind of cluster measures that you choose, right. Cure might be able to give you or might not be able to give you this kind of clusters, depends on again how your sampling that you do and what you start off with and so on and so forth. So whole bunch of imponderables. But again the same thing with NDB scan, depending on your choice of min points in epsilon, right, you might get very weird results, right. Yeah. So if you look at the data mining textbook by Hahn and Camber, right, Michelin, Camber, Hahn book, right. So they have actually horrendous examples of DB scan. In fact, I think they did a significant optimization to find out which are the worst parameters possible for min points and epsilon, and they give you results because they wanted to write a paper that said, hey, we have an algorithm that does better than DB scan. So they said, oh, DB scan can perform really badly if you give it bad parameters. So let us give it bad parameters and then we will beat it. Right. So I mean, well, just assuming that they were actually being more fair than that, but the way look at the results, it looks like that. I mean, DB scan looks really horrendous, and their method, which is called chameleon. Huh?
Abbreviation?
It's an acronym, yeah. So I think C stands for clustering. I'm not sure about I'm not sure about that either. So yeah, it's an acronym. Did DB scan, right? I just start off with some arbitrary point, and then I look at examine the clusters and so on and so forth. So what happens if I happen to start off at a boundary point instead of a core point? I'll examine it, I'll say, okay, it's not a core point, I'll throw it away, right. So it will never get assigned to any cluster, so it will kind of be all by itself as an outlier, even though it should belong to a particular cluster, right. That is one thing. The second thing is, suppose I want to vary epsilon and I want to run the clustering again, I basically have to do it all over from the beginning, right. So what optics does is gives you a clever way of ordering your data points such that, right, for different values of epsilon you can recover the clusters very quickly. For the same value of min points, the min points is fixed, but epsilon changes, right. So it gives you a way of ordering your scan through the data such that for different values of epsilon, okay, I can recover the clusters very quickly. It's a really cool idea.